Welcome back to another lesson in AP Calculus. This is Unit 7 about integration and the definite and indefinite integrals. Today we're going to be looking at some additional formulas for indefinite integration. Let's start off with just some practice problems. I'd like you to find the indefinite integral of these problems here, and then we'll go over our work. And I think that's x to the negative 1/3. That one looks a little hard to read, but otherwise I think you can do them. Pause the video and give it a try. Okay, let's see how you did. You should have increased the exponent by 1 and divided by the new one. And don't forget plus a constant c. All right, on this one I recommend rewriting this as x to the 2/3 dx. Then when we integrate, we're going to raise this by 1. So add 1, meaning add 3 over 3, giving you 5 over 3. And multiply by the reciprocal. So instead of dividing by 5/3, that would be the other option. I could divide by the new exponent. But we don't like to divide by fractions. We instead like to make it to where we times by the reciprocal. So that's why I do that. You could think of this as multiplying by 1/5 as well. So that's why I say I always divide by the new one or multiply by the reciprocal of the new one. Same thing. All right, let's rewrite this as x to the negative 5th dx. Okay, up the exponent by 1 and divide by the new exponent. And then don't forget plus c. All right, this one here, again, I recommend rewriting as x to the 1/2 dx. Now up the exponent by 1. And multiply by the new exponent's reciprocal, plus c. All right, this one here rewrites as x to the negative 1/2 dx. Up the exponent by 1 to get a positive 1/2. Multiply by the reciprocal to just get 2 times it. Okay, on this one here, we're going to raise the exponent by 1, so add 3 over 3 to negative 1 over 3 to get 2 over 3, and multiply by 3/2. And don't forget plus c. So I'd like you to consider the following integral expression. Why does this power rule that we've just been using not work in this situation? Take a second and think about that. All right, well, maybe you do try and rewrite this. Let's say we try and rewrite this as the integral of x to the negative 1 dx. Well, then, if I increase the exponent by 1, I get x to the 0, and then I have to divide by the new exponent. But is that allowed? No, I can't divide by 0. So it doesn't work. It doesn't work. Why doesn't it work? Because we can't divide by 0. But luckily, there's another way we can do this. Let's think about what has a derivative of 1 over x. Well, you might remember that the expression the natural log of x has a derivative of 1 over x. So we would think that the integral must have something to do with that. However, because of domain restrictions, the formula actually requires the absolute value of x. So let's see. What is the integral then of 1 over x dx? The answer is the natural log of the absolute value of x plus c. A closely related integral that we need to think about is the integral of e to the x. So again, I'll ask you, what function has a derivative of e to the x? Well, you may remember that the derivative of e to the x is e to the x. It doesn't change. So we should not be too surprised that the integral of e to the x dx is e to the x plus a constant. All right, let's practice. Okay, so I'll do each term. The integral of e to the x is e to the x. The integral of 1 over x is the natural log of the absolute value of x, then plus c. Now on this one here, that's x to the negative 1. That's the 1 over x. We can't do the power rule. It's just the natural log of the absolute value of x. Minus 3 is a constant. We can just come along for the ride. The integral of e to the x is e to the x plus c. All right, let's do some rewriting here. This will be x to the negative 2 plus x to the 1/2. And I can rewrite this, but I actually just, when I know that it's 1 over x, I just leave it like that. For some reason, it helps me remember to use natural log. All right, so when I raise the power of 1, I get x to the negative 1 over a negative 1, which is just negative. Plus, that becomes x to the 3/2 times 2/3 minus the natural log of the absolute value of x plus c. All right, let's take a look down here. The integral of cosecant squared x. The integral of cosecant, well, what has a derivative of cosecant squared? That's cotangent squared. And if it has a co in the answer, remember it's negative. So it's cotangent x minus, and then the 5, again, will just come along as a constant multiple, times the natural log of the absolute value of x plus c. All right, let's take a look at this one. The integral of cosine x is sine x. And the integral of secant tangent, what has a derivative of secant tangent? Secant. So secant x plus c. All right, this one over here I'm going to rewrite as the integral of 2 e to the x minus x to the negative 2 dx. When I integrate, it's 2 e to the x minus x to the negative 1 divided by a negative 1 makes that a plus, and then a c. Along with the integral formula for e to the x, we also need a formula for other bases. The integral of a to the u du is a to the u over the natural log of a. And the reason why that is we need that over the natural log of a to cancel the times natural log of a that we get when we take a derivative. So in summary, let's compare our derivative integration rules. The derivative of the natural log of u is 1 over u du dx. So the integral of 1 over u du is the natural log of the absolute value of u plus c. Now, we also have a log with other bases, which is really just a change of base formula. But the log base a is simply 1 over u, just like the natural log of u, but then also divided by the natural log of a. Notice I don't have an analogous integration rule for that special case because that natural log of a, that's just a constant of 1 over natural log of a, so it doesn't change anything. We know that the derivative of e to the u is e to the u prime, so it should make sense that the integral of e to the u is e to the u plus c. We do have to have this special formula for a to the u. A is some other base, so like 3 to the u. The derivative is 3 to the u times the natural log of the base. So when we have to integrate a to the u, we need to have that divide by natural log of a to cancel out that natural log that we get when we took the derivative. Because whatever we integrate to, its derivative should give us this back. And if I took the derivative of this, it would be a to the u times natural log of a, and I would need this natural log of a in the bottom to cancel it out. All right, let's evaluate the following integrals. Pause the video and give it a try. Okay, let's see how we did. The integral of sine x is negative cosine of x. Remember, when you integrate, if you get co in your answer, make it negative. The integral of e to the x is e to the x, and then plus c. On this one here, you should have just raised the exponent by 1 and divided by the new one. Since I've already got a denominator of 2, they just multiply. And the integral of 2 to the x is 2 to the x divided by the natural log of 2, because of the rule for bases other than e. All right, this natural log of 2 here, I threw it in there just to remind you that the natural log of 2, that's just a constant. So it just comes along for the ride as a constant multiple. So the natural log of 2 times x to the 4th over 4 minus the natural log of the absolute value of x plus c. Okay, so now if you would please try these practice problems. All right, let's see how we did here. So we have a differential equation. We're just going to integrate both sides. So the integral of f prime is just regular f of x. The integral of cosine of x is sine x. And the integral of e to the x is e to the x plus c. Now we can use our initial condition that f of 0 equals 3 to plug in and solve for c. The sine of 0 is 0, and e to the 0 is 1. So 4 is equal to c. So now we can state our final answer is that f of x is equal to the sine of x minus e to the x plus 4. All right, let's take a look at our next one. This integral is f of x. The integral of cosecant cotangent is negative cosecant x plus 2 times the natural log of the absolute value of x plus c. And we're told that f of 1 is 4 minus cosecant of 1. So I'm going to put 4 minus cosecant of 1 where f of x is, and I'll put 1 where x is. Well, the natural log of 1 is 0, and those can just cancel out. So what we get is 4 equals c. So our answer is f of x equals negative cosecant x plus 2 times the natural log of the absolute value of x plus 4. All right, now in this next one we have a second derivative differential equation, so I need information about the derivative and the original. We'll integrate to get the first derivative, and I get x cubed over 3 times 3 will cancel, plus 4e to the x plus c. I'll replace f prime with 5 and put a 0 in for x. Now recall that e to the 0 is 1, so this becomes 4 plus c, so c equals 1. So that tells us that f prime of x is equal to x cubed plus 4e to the x plus 1. Let's now find f of x. So we'll integrate again, and I get x to the 4th over 4 plus 4e to the x plus c. But we know that f of 0 is 3, so this is 3 is equal to 0 plus e to the 0 is 1, so 4 plus 0 plus c. So c equals negative 1. So f of x is x to the 4th over 4 plus 4e to the x plus x minus 1. All right, let's take a look at practice 4.4. A particle moves along the x-axis at a velocity of 3 over t plus the square root of t for t greater than 0. At time t equals 1, its position is x equals 1. Find the particle's acceleration function. Okay, make sure you've done that. All right, the acceleration is the derivative of velocity. So my acceleration just requires me to take the derivative, which makes this negative 3 over t squared, because that's 3t to the negative 1, plus that's t to the 1/2, so it becomes 1/2 t to the negative 1/2. And that's our acceleration. To find the particle's position requires us to integrate. So that becomes 3 times the natural log of the absolute value of t, plus that's t to the 1/2, so it becomes t to the 3/2 times 2/3 plus c. Now we know that at t equals 1, the position was 1. So 1 equals 3 times the natural log of 1 plus 2/3 times 1 to the 3/2 plus c. The natural log of 1 is 0. 1 to the 3/2 is 2/3, so 1 equals 2/3 plus c. That means c is 1/3. So our position function, we can call it s of t or x of t, since it's on the x-axis, is 3 times the natural log of the absolute value of t plus 2/3 t to the 3/2 plus 1/3 for t greater than 0, since that was our original restriction. And because t has to be greater than 0, I don't actually need the absolute value bars. Okay, let's look at one last question. A particle's acceleration function is given by a of t equals cosine t minus e to the t. The particle's velocity at time t equals 0 is 5. The particle's position at t equals 0 is 1. Find the position function s of t. Pause the video and give it a try. All right, so I've got the acceleration function. I can get the velocity by integrating. Since acceleration is the derivative of velocity, velocity is the antiderivative of acceleration. So this becomes sine of t minus e to the t plus c. We know the velocity at t equals 0 is 5. So 5 is equal to the sine of 0 minus e to the 0 plus c. Sine of 0 is 0. So this is just negative 1 plus c, so c equals 6. So v of t is sine of t minus e of t plus 6. Integrating again gives me position, making this a negative cosine of t. When you integrate, if you get co in your answer, make sure it's negative. Minus e to the t again, the integral of e to t is e to the t, plus 6t plus c. We know the particle's position at t equals 0 is 1, so I'll plug in 0 for t, excuse me. All right, cosine of 0 is actually 1, so this is 1 equals negative 1. E to the 0 is 1, so minus 1, plus c, so I get 3 is equal to c. So s of t equals negative cosine of t minus e of t plus 6t plus 3. And that is all she wrote.